Hello, everyone. My name is Bora Ulaş Bakandı. I'm the leader of Group 4. And today we're going to be doing our final model presentation. My teammates are Mahmut, Furkan, Bakal, Doğan, Berkay, Sözer, and Zeynep, Nedret, Ulaş. So as a final recap, our data set is a collection of ultrasonic distance readings and sensor readings to help train a robot navigation algorithm. As you can see in the figure, this is meant for interior spaces, such as living rooms and other domestic environments. This data was taken from Kaggle, and you can see the link right there. Our goal with this data set is to first develop a robust model to assist a wall-following robot in traversing a room. Secondly, to consistently evade hindrances and impediments in its environment with precision. So we're talking of like, and it must consist both concave and convex accuracy, since it's circular fashion follow of the room. We are also curious to see how this more traditional navigation algorithms on the market, commercial market, which instead of navigating in real time using machine learning, have to scan their environment or use programs. When we first received of 5.4K samples, foreigners, and one category with 4 classes. This height, our requirements, we need around 10K samples, and even that is slightly low. So we have to use oversampling to overcome this deficiency, improve the number of outcome classes that we have later.
Bora, I have difficulty hearing you. Does everybody have problem with the hearing, Bora, or just me?
No. Sounds
I
okay.
can hear him clearly.
Clear? So I think I have a problem. So I cannot hear you. Maybe, okay, let's try again. Continue. Okay, thank you.
Okay. Again, our obviously, as you can see, it is not. So we can see that our third, our fourth classes, which correspond to which corresponds to no turn, a slight right turn in this case, are significantly underrepresented in this data set. This corresponds, we can see that it's correlates with a single direction of turn, where the robot might be biased towards turning, for example, clockwise instead of counterclockwise, if the way the data set was received was in one single direction. So it is required to do these much less often. These outcomes are very underrepresented, and we can see that while turning in one direction in one magnitude is around 2,000 samples, the other is 300, 800 samples, which is not enough. It's very unbalanced. So we're going to have to use oversampling methods to overcome this imbalance. And we will also have to overcome our lack of samples. Now, Zeynep will continue with how we overcame these obstacles.
So in order to improve our data set, we wanted to increase our data. We use SMOTE to do synthetic minority oversampling. And we mirrored our right turns to create a new class. This way we increased our numbers and we made our data set balanced with SMOTE. Next, please. After applying these implementations, you can see here that our data set is now balanced and we have 11,000 data. Next, please. And these are our accuracy scores for train and test before applying anything with 5.5K data. It's 93.2 for train and 86.4 for test. After we applied these, and we obtained 11,000 data. Our train score increased to 96.9 and test score increased to 93.6. Next, please. For feature engineering purposes, we combined some features to create new features. In method 1, we created 6 features, and in method 2, we created 8 features. These are for you to help visualize what we did. Next, please. And you can see here that in method 1, there are 6 new features and which ones we combined to create them. And on the right is for method 2 and what we did and which ones we combined. Next, please. So in total, we used KNN K3. So our initial data set had 93.2 accuracy score for train and 86.4 test. After SMOTE and new class, we increased our train and test scores. And we applied method 1 and method 2 separately, and then we combined them. Method 2 seemed to have a higher score than method 1. After combining both, the results were higher for both. So they were better. Now, Berkay is going to continue.
Hi. Before starting the hyperparameter tuning process, we first divided data in our dataset in two. These are the train data for 90% and the data for the test for 10%. And we divided our train data in two again. These are the train data and the validation test data. Next, please.
Berkay, may I ask a question?
Yes.
First of all, thank you for that clear and understandable figure. So we are sure that you understand how to apply the data speed for hyperparameter tuning and model selection. Thank you for that. My question is that did you save, after splitting the data in such way, did you save each partition into a file or not?
We didn't save it in a particular file.
Okay.
Should we?
No, I was about to ask that if you are you sure that you all for all the models and for all the different hyperparameter values, are you sure that you use the same partition of the data for train, validation, and test? Are you sure that?
No, actually, we didn't do that. We did this after the receiving feedbacks from you, and we split our data according to that.
Okay, so what I said that after splitting the data, you have to freeze these partitions. So in the train data, if there are 8,931 samples, these samples must be frozen so that every model with different values for the hyperparameter parameters, they should see the same set of data, set of samples. Did you guarantee this? Did you ensure this? So one of the ways to save these 3 parts of the data into 3 separate files. When it needed, you just upload it or load it and use it. Do you understand my point?
Yes, I understand your point. Thank you.
Did you do it in that way or did you do on the fly?
We did that. We did the same way you talked about, I guess.
Okay. Please continue.
Okay. First of all, we would like to share our KNN model with you. We initially started with the default K value, which is 3, but we weren't sure how to optimize this value. We experimented with increasing and decreasing the K values 2 at a time. And next, please. And as a result of the trials, the categorical accuracy, we achieved the highest accuracy at this point with the K equals 3 and 5. But we want to use K11 because we got the sweet point in K11 points. So our sweet point is K11. And next slides. And also we checked the F1 validation score, and we reached the same conclusion in the F1 as in categorical accuracy. Yes, next slide. And
May I ask a question, Berkay?
Yes.
In the previous slides, in both of them, you said that you choose 11 as the key parameter. Why?
Because it is the weakest point. It is the closest point where the train and the test validation score is the closest.
Yes, but the sweet point definition, I mean that not overfitting, not underfitting. Do you think that when K is 3 or K is 5, do you think that there is overfitting or underfitting?
There might be an underfitting or overfit. There might be an overfitting in the K equals 3 or 5.
So
But
Zeynep,
in the K equals 1,
okay. Let me ask Zeynep. Zeynep, do you think that on that slide, according to the result, do you think that K3, when K is selected as 3, do you think there is overfitting risk, Zeynep?
No. I mean, yes, but like we can use it, I think. The difference is not that much between train and
Furkan.
I think also, yes, they are very close points, and they not might be in here overfitting, but we want to select the closest one, actually.
But there is no such a rule, right?
Yes.
During the class, we didn't discuss this as a rule, right? So we didn't say that the train and the validation must be the same and we select this as the sweet point. We didn't say this, right?
Yes.
Bora?
I think our aim was to reduce the discrepancy between train and validation data, but I understand there might be some.
So if I
room.
were you, most probably, I would choose K3 because the validation is high, and as I see from the figure, K1 is okay, totally memorization, right? Because the train data is 100% is right. So what we expect from K is 1 is automatic like that. But for the K3, it looks like that it is far away from memorizing the data, 96 point something, right? And the validation is not too far away from the train data accuracy. So do we agree, Berkay?
Yes.
I were you, I wouldn't continue with K11 because K11 is 2% is less than for the validation than when K is 3. Do you understand my point?
Yes, I misunderstood before, but now I understand.
Yes, yeah. So please, I would like to clarify that we don't select the hyperparameter key for KNN or for another model when the train and validation are the same accuracy. There is no such a rule. But you need to discuss overfit, underfit carefully. But for me, K11 is underfit. Do you agree, Zeynep?
Yes, hocam.
Do you see that K11 is underfit? Do you see that?
I mean, they're almost the same score, so yes, I think.
No, it is not being the same score. So if you check that hyperparameter K is 9, you get better result. K is 7, you even get better result. K is 6, even get better result. So why you agree with having less result with K11? What's the point? So it is, you see that in the graph, you are getting less and less accuracy. So it is underfitting. Why you choose the K11 then?
We should have chosen K3.
Bora?
I think we could probably get away with a lower K3, 5 maybe.
Yes. But in your team decided to present this as a final result, final decision of hyperparameter value.
In retrospect, yes, probably 3 or 5 is better, but at the time we want to minimize that difference between.
But there is no such a rule, right? Okay.
Well, that's our mistake. So,
okay, Furkan. So, are you gonna update this in the final report?
Yes, we can update.
Okay, please continue.
Okay. And for the logistic regression, we decided to use L2 regularization, and this is a technique used to prevent overfitting of a classification model, and it helps to prevent the model from overfitting to training data and therefore not generalizing well to the new data. And next slide. And in our analysis, we experimented with a range of C values for L2 regularization, spanning from 0.001 to 500 in the logistic regression model. The L2 regularization method was selected for its strength in handling multi-collinearity and its capacity to distribute weights evenly across the features. And
May I ask a question here?
Yes, sure.
Berkay, I will start with you, okay, again. So, for the logistic regression, if you are talking about changing the parameter C, alpha, I am sorry, right? Alpha. With the alpha value, how it's suggested in the documentation to change the alpha value? In which scale? Here you are incrementing randomly, I believe, 2, 10, 20, 50, 75, 100, 150. So in the book or in the class, how we suggest you update, try alpha values? Do you remember?
I don't. Yeah, I'm so sorry. I don't.
Okay. Ulaş, Bora?
This would normally be a logarithmic sort of scale.
Bravo. It must be logarithmic scale, right? So to the base 2, so you need to try 10, 100, 1000, for example, or 0.1 or 0.1. If you check the graph, you see that there is not so much change when you increase arithmetic. For example, plus 50, plus 50, plus 100. Do you notice that?
Yes.
Do you notice that? Yes.
Yes, we still wanted to represent the
but
valid.
The science says that because alpha is there as a multiplier. So in the book and in the class, we discussed that you need to check alpha with the logarithmic scale base 2. Okay? 10,
Okay.
Yes.
100, 1000, kind of. 0.1, 0.1, 0.1. Do you understand my point?
Yes.
And if you check this scale, you understand that you see that it's almost linear with respect to arithmetic increase, right? But if you use logarithmic increase, you would see the change. Do you understand why you don't see the change here now?
Yes.
So you need to understand the parameters. According to that, you need to update and search for the different values and performance change. Please continue.
And after examining the categorical accusation results in here, we decided to use 10 as our alpha value because it is the smallest and the highest possibility to guessing it's right, guessing our model right. And next slide, please. And also in the F1 validation score, we use the 10 again because it is the same reason for why we choose in the categorical accusation with 10. And Furkan will continue.
Thank you, Berkay. Hello, I am Furkan. Today I will talk about the random forest model. And in the last presentation, we had a problem with the train source, but this week we rearrange it as you pointed out. And in the random forest widget in orange tree, the important parameters to adjust are the number of trees, number of attributes, and pre-pruning options like limit depth. Next slide, please. Firstly, we compared our results on the some values to find our number of tree. And for number of tree, larger is always better, actually. But in this chart, as you can see, both in the value 13 is our nearly highest and our sweet point. Next slide, please.
Furkan, may I ask something?
Of course.
So to present a result such a situation. I mean that if you are trying multiple parameters to optimize, right? You need to mention when optimize one parameter, you need to tell about us that what is your default values for the rest of the parameters.
Yes, you are right. The default parameters are which when we use this widget on the orange tree, the orange tree came to us in some default parameters, some default values. We use these values for the default
But
values.
in the presentation, in your final report also, you have to first present that these are my default values, but for each parameter, I will do a grid search. So when I mention about one parameter value, please remember that, note that the other parameter values are kept fixed for
Yes.
that points.
Yes, you are right. In the last presentation, we put it, but in the suggestion we forgot.
When you presented results, you have to first mention about that. All right. In your final report, please fix it.
Next slide, please. And then we compared the results of some values to find out the number of attributes using some values. Using the value of the 13 is which we reach from the number of 3. And number of attributes is calculated by the square root of the number of features for classification. And in our datasets, we have nearly 38 features in our dataset. So we get about nearly 6 values for this formula. But as you can see in the table, while the number of tree value is 13, in the CA and F1 score in both of them, we got the highest result with number of attributes 5. So we choose this 5 value for this. Next slide, please. And after that, and next slide, please. Again, that's our F1 score, and we got the same result. And now it's time for a pre-pruning operation. Using pre-pruning, limit depth or do not split subset smaller than pre-pruning operation might sometimes improve the performance. And in this chart, you can see the result of the fine-tuning processes we applied on the limit depth. And for categorical accuracy and F1 score for both of them, we got the highest result on depth 9 value. And next slide, please.
May I ask a question here?
Of course.
For the F1 score or in the previous one, what was for the score? Classification accuracy?
Categorical accuracy.
Okay.
Accuracy.
Classification accuracy, right?
Classification accuracy,
So
yes.
how can you interpret that when depth is greater than 15, then your train performance is 100%? How can you interpret this? How can you explain this?
And after that, when we increase our depth value, our model is going to memorize these values.
How?
And I think when we increase the depth value, the random forest uses decision tree also. And when when we increase our depth, I think how can I say?
20, 25, okay. What you should understand from that about your trees? What would you understand? Zeynep?
It's too deep. We have to
So when it's too deep, what happens?
overfit.
I see it is overfit, but how? Mechanically, if you know the algorithm, how can you tell us that? What happens in the tree?
Every single data point is there.
Yes, but
It knows that.
so Bora?
I mean, I'm thinking the same thing. I think it's overfitting. Just
yes, it is overfitting, but I am asking that overfit can happen, for example, in SVM as well. But I am asking if the overfit happens in 100% in a random forest or just a decision tree, what happens mechanically inside the decision tree actually? My question is that. Berkay?
It's memorizing.
No, I see what
Pure
I'm
nodes.
asking again. When it memorizes, what happens actually in the decision tree structure?
All of them are pure.
The R leaf is memorize something. The pure.
Yes, that's the
R
answer I am looking for. Actually, if it's 100% true, so actually every left node either must
pure.
be right, must be
Yes.
pure left node. Am I right? Remember
Yes,
in the
sure.
class, the pure means that in the classification, actually
100% right.
there is only samples from single class. Am I right, Berkay?
Yes.
Okay. Bora, Zeynep, do you remember?
Yeah, hocam, I also just said it, but
No,
you didn't hear
say.
me.
Did you say pure terminology?
Yeah, I said pure.
I couldn't hear. Anybody else? Anybody hear that pure? You said that something different. Memorize or something. Am I
No,
so?
after that, I guess you didn't hear it, so it's fine, but I get it.
No, I didn't hear because you try to explain the overfit, blah, blah, memorize, but the terminology I am looking for is the pure.
Yes.
Okay.
Pure. The keyword is pure, not
Pure.
another English word. Right? Okay, let's continue.
Next slide, please. And finally, we did the same process for the do not split subsets smaller than pre-pruning operation, and we got the highest result with a value of 5. And next slide, please. And in F1 score, again, we got some results. And next slide, please. And finally, you can see the results of the fine-tuning processes we have done on the 3 models so far. And according to these results, we choose the random forest model as the most accurate model for us datasets, we think like that. And next slide, please. And that's for the test data. The before slide is for train data, and now it's for the test data. We correct these words. In the last presentation, we use wrong word for the train and validation. And next slide, please. And finally, that's our confusion matrix for our 3 model. And again, in the random forest model, we got the highest results for the classification of each class. And we select the random forest model for our dataset. That's all.
Veya konuşuyorsunuz, mikrofonunuz kapalı hocam.
Can you show the confusion matrix? Okay. Confusion matrix.
Next slide.
Next.
Confusion matrix.
The last slide.
Last slide.
Yes, okay. So I would like to ask a question for you. For the random forest, Furkan, for the class 1, what is the class 1 actually? It is turn right, turn left. What was it?
Forward.
Forward?
Forward.
Okay.
Forward.
Yes.
The class 1 is forward. So how many what is the percentage of you misclassified instead of go forward?
Sharp right.
Well, I'm asking Furkan.
I'm sorry. I'm sorry.
Can you ask again?
The class 1 is go forward, right?
Yes.
And you sometimes misclassified the next move. Instead of go forward, you select something else, right?
Yes.
So what is that? According to that chart.
According to that chart is
So what is the highly probability?
Second, third, and fourth class. We predict some.
Which one is the highest probability? You say that instead of go forward, you said what?
The third class, as I understand, the turn right, slide right, as I understand. As I
You understand this? Okay, let me ask. When your model predicts go forward, actually, sometimes it makes mistakes, right?
Yes, it
What
can
is that,
be
what is
wrong.
that mistake it does? What it confuses with? Go forward, the first class with which one mostly? Or which one? When it
Mostly
predicts.
third class, turn right.
Do you understand, every team member? Do you understand my question? When your model predicts go forward, which is the first class, actually sometimes it makes some mistakes. So which class it does make confusion mostly? With which class?
Sharp right, the third class.
You said third class. Furkan said third class. Zeynep?
I think 4.
4. And Bora?
If you mean if we look at the table on the right, it's the fourth class, if I'm not misreading.
Yeah, it is the fourth class. Why? Because the columns are predictions. Am I right?
Yes, yes, you are right.
The predictions.
The rows are the actual
rows
values.
are actual values.
Yes.
Right?
Yes.
So in your prediction, 1.4% is confused with fourth class, and the rest are correctly predicted. Am I right? That was the question. Berkay and Furkan,
you are right.
Okay. All right. So please specifically tell me what you decide. So you decide to use random forest with these parameter values?
Yes, we decide using random forest model.
Okay. Do you want to add anything to your presentation?
No, that's all. Thank you for listening.
Okay. Thank you for the presentation. I hope you will fix the points that I pointed out in your final presentation report before the finals. Okay. So, thank you.
Thank you.
Thank you.
Thank you.